Hi, Mr. T here. In this video we're going to look at molecular shapes, and we're also going to look at how to calculate whether a molecule is polar or not. We're going to do that using dipole moments and working out the overall polarity when we add those up. And we're specifically looking at larger molecules, ones that have 5 or 6 electron density regions around the center atom. This is there to support level 3 NCEA Chemistry 3.4, but it will also be helpful for anybody wanting to explain or work out whether a molecule is polar or not. Okay, let's get going. Okay, so up until this point, if you're watching this video, you should be familiar with shapes that are based on tetrahedral and shapes that are based on trigonal planar. Those shapes you might have had practice writing and explaining why they have the shapes that they do and why they do or do not have a polarity. So when I talk about tetrahedral base shape, what I'm saying is we have an atom in the center that is surrounded by 4 electron density regions. When they repel against each other, because they are negative and they mutually repel each other, because they're opposite they're similar electrostatic charges, so they will push away from each other equally to produce this angle of 109. And in a 3-dimensional arrangement, this is a tetrahedral shape. Now, if we keep this base shape or the skeleton framework, we can get a couple of different shapes that originate from this. So another one that does is called our trigonal pyramid or trigonal pyramidal. Now, what it still has 4 electron density regions. Apart from one of the electron density regions is non-bonding electrons and 3 are bonding. Now it produces a 3-dimensional shape that looks a bit like a triangle pyramid, so it's called trigonal pyramid. The other shape that is produced from this same framework, or the base shape, is a bench shape. Now the bench shape also has an angle in here of about 109 degrees. It has 2 non-bonding regions and 2 bonding regions. So that's when we talk about what we may have learnt so far, you might be familiar with those shapes. So the new shapes that we're going to learn is 3 shapes based on the trigonal bipyramidal base shape. Now a trigonal bipyramidal is a shape that is produced when we have 5 electron density regions around a central atom. When they repel from each other as much as possible, they produce a shape that has 3 of the atoms around the middle, making a trigonal planar shape, and then one going directly up and one going directly down. Now we can think of this as 2 trigonal pyramids with their bases joined, which is why it's called a trigonal bipyramid shape. It has angles of 109. This is the angles of the 3 that are on the plane around the center, or 90 degrees if it's between the 2 atoms that extend up and down towards the plane. Now we can get 2 other shapes with this. There's actually more than 2 other ones. There's a 3rd one as well, but we'll just go with 2 basic shapes here, with the seesaw or distorted tetrahedral shape. So if we remove this chlorine right here, so we remove this one because it has the 90 degrees, so this is the first one to be removed. And if we just rotate it 90 degrees, we see it looks a bit like a seesaw, or what Americans would call a tita tota. It has 1 non-bonding region and 4 bonding regions. Obviously the one at the top here is a symmetrical shape. This is an asymmetric shape. We have, if we take away 2 of these, this one and another chlorine in the middle, we ended up, if we rotate it, with a T shape. So this is just called T shape. It has 1, 2, 3 bonding regions and 2 non-bonding regions. So we have trigonal bipyramid shape, we have the overall shape of trigonal bipyramid, and 2 associated shapes, seesaw and T shape. Both of these are asymmetric. Then we have an octahedral base shape, which is, the name is unfortunate because there are only 6 atoms that come off. Octahedral is actually based on the amount of faces that this three-dimensional geometric shape has. It has 6 corners, but it has 8 faces. Now every angle between every bond in this shape is 90 degrees. And every atom has on the other side of it a corresponding atom. So if you have the same atoms attached to this, this is always going to be symmetrical. This is called octahedral. If we only have 5 of these 6 bonding regions and 1 non-bonding region, we have a square pyramid. So you can imagine there's a square planar along the bottom here, and then 1 atom that goes upwards, and we can draw the lines that associate with a square pyramid like pyramids at Giza. Asymmetric, this shape here, the square pyramid. If we take away the top one and the bottom one, we're left with a square planar shape, or square planar shape. These fluorine atoms here are still directly opposite each other. So this is a symmetrical shape. So this is an outline of the basic shapes, and the 6 new shapes are the ones on the right here that we need to learn. Okay, just a couple bits of information before we start. So this tetrahedral shape has angles, if I'm more specific, of 109.5. If I actually draw the ammonia, which is a trigonal pyramid shape, it is one of the shapes from this base shape, where we have 1 lone pair or non-bonding pair on the top, we notice that the angles, corresponding angles, are a wee bit smaller. And if we go to the water, they're a wee bit smaller again. So they go 109.5, 107, and 105. Now the reason that these angles get a wee bit smaller is to do with this non-bonding influence here, these lone pair. In fact, these lone pairs just repel a bit more than the bonding regions do because they're less constrained. So they end up pushing these bonding regions a bit closer together. It's not much, but it's a little. But if we have 2 of them, it's a bit more, and we get 105 degrees. So these are non-bonding pairs, and they have a bigger influence on repelling than the bonding regions do. Now, we usually ignore that when we draw our shapes, but if someone asks us a specific question about this, we can justify why these angles will be a bit different now. Okay, and the next thing we need to know just before we go and look in these shapes is what a bond dipole is, and what dipole moments. So if we have 2 atoms bonded together, and these 2 atoms have a difference in electronegativity, and in this case chlorine is a lot more electronegative than hydrogen, when they share electrons, chlorine has a larger share of the bonding electrons, so it gets a dipole moment of slightly negative. So this wee delta here, and sometimes when we draw it by hand, it looks more like not quite completed figure 8. So this delta minus says that the chlorine is a wee bit more negative than we would expect because it shares more of the electron. And we get a dipole moment for a hydrogen with delta positive. Now, this remember, is from an uneven share of electrons because they have electronegativity difference. Now this produces what we call as a bond dipole, and we can draw a representation of a bond dipole by drawing an arrow with a plus at the end where it's positive, and the pointy end is where it's negative. So we can use that to direct the direction of the negative charge. Okay, so let's look at specific examples here. The first one is the T shape. Now you might remember that the T shape was based on the trigonal bipyramid base shape. Now the reason for that is there are 5 electron density regions around the center that will produce, when these regions mutually repel as far as they possibly can, it'll produce angles of 90 and 100 degrees and a base shape of trigonal pyramid. Because 2 of them are non-bonding, the 3 are bonding, the T shape is the shape that is produced. Now if we draw these T shapes out here, just redraw them again so we can actually put in the dipole moments. If I look at the chlorine and the fluorine on the periodic table, I can see that the fluorine is more electronegative than the chlorine because it's further up the periodic table in this group. So it will have the dipole moments of slightly negative. This will the chlorine and the fluorine are sharing electrons. Fluorine is more electronegative, so it gets a bit more of the negative charge of the electrons, so it gets slightly negative, and the chlorine is going to get slightly positive. Now when we look at the fluorines and how they're arranged, the center of these three, so if I was to draw a triangle between these three negatives, and the center of the triangle is right here, and that's the center of where this negative dipole moments are, the negative charge. Now you'll notice that the center of the negative charge is here below the chlorine, and the positive charge is right in the middle of the chlorine. Now these poles, these are said to be the poles, the center of the positive and the center of the negative. It's the positive pole and the negative pole. Now because these poles are in two different places, this molecule is said to be polar. If we were explaining the way that I taught you in an earlier video, which is for level 2, you would say that there are three bond dipoles arranged asymmetrically, so the bond dipoles don't cancel out. We can still say that these negative and positive charge don't cancel out because the poles are in different places. That's not a bad idea to put that in. Okay, so let's look at the next shape. It's called seesaw. So here again, it is based on a trigonal bipyramid shape because there are 5 electron density regions. Because 4 of them are bonding and 1 is non-bonding, we get this seesaw shape or distorted tetrahedral. When we look at this shape, it appears to be asymmetric. It is. Look on the right here in this representation of this molecule. Let's put the dipole moments in. We can see the center of the positive dipole is in the center of the sulfur atom, and we can see the center of the negative dipoles is slightly below the sulfur. When we account for all of these 4 dipole moments, we can see the negative pole, which is accumulation of all the dipole moments that are negative, is slightly lower than the positive pole. So therefore this is going to be a polar molecule because the negative pole and the positive pole can't cancel out. They're at different places. They have poles. So let's have a look at this one here. Oops, so it looks like I've put the poles in at the start. Here is again a trigonal bipyramid base shape, but every single one of these bonds is every single one of the regions is a bond, so it is going to have the same overall shape as its base shape. Now remember, there are 5 electron density regions. They mutually repel as much as possible to produce angles of 120 and 90 degrees. We've got this base shape of trigonal bipyramid, and we have the overall shape of trigonal bipyramid. If we redraw these here and we put in the dipole moments, here they are. Every chlorine has a slightly negative charge because of the bonded dipoles between the chlorine and the phosphorus. The phosphorus has a slightly positive charge, but the center of all the negative charges and the center of the positive charges are in the exact same place. Therefore, we do not have poles. There is no negative and positive pole. And you could say it another way. You could say that the negative charge cancels out the positive charge. But the reason we call it non-polar is because there are no poles. The center of the negative and positive are in the same position. Okay, so let's have a look now at some octahedral base shapes. So in this case, we have 1, 2, 3, 4, 5, 6 electron density regions mutually repelling as much as possible. We produce angles of 90 degrees, and it's a base octahedral shape. So we have to imagine that there was something going up and down. This is the framework, octahedral. But because 4 of the regions are bonding and 2 are non-bonding, it's said to be square planar. Okay, so let's draw these shapes again here, and let's put in the dipole moments. The fluorine is more electronegative than the xenon, so the fluorines are going to get the dipole moments of minuses, and the xenon is going to get a plus dipole moment. Now we can see that this molecule is actually symmetrical, and you can see the center of all of the negative charge is in the center of the xenon, and the center of the positive is in the center of the xenon. So we have a molecule that doesn't have poles because the poles are in the same place and they cancel out. So overall the molecule is polar because the poles are in the same place. Square pyramid. Let's have a look at this one. Okay, again we have 6 regions of electron density. They repel as far as possible to produce this octahedral shape is the base shape, 90-degree angles. But because only 5 of the 8 regions are being used, we're going to have a square pyramid. Okay, so we've got a square base and the fluorine at the top that gives us a pyramid shape. If we draw these out, now you can see that this square pyramid is not going to be symmetrical. The center of all these yellow atoms here is not in the center of where the purple one is. So if we assume that the fluorine is more electronegative than the iodine, which it is because the electronegativity decreases as we go down its group, and iodine is 2 further atoms down, then we can see that the center of the negative dipole moments are on the fluorines and a positive dipole moment on the iodine. We can see that when we do the center of the negatives, they're going to be slightly above the iodine. So see the negative pole is slightly above the iodine because this fluorine at the top just pulls the center of the negative pole at the top away from where the positive pole is, which is in the middle of the iodine. So now we have a negative and a positive pole, or 2 poles. They do not cancel out, so this is a non-polar molecule. Okay, so the last one we need to know for this set is, here is the octahedral shape. So this is the actual base shape that everything is based on, and there are 6 electron density regions pushing away as far as possible. We have angle of 90 degrees. It produces this octahedral shape. All of the regions are bonding, so the overall shape is also octahedral. If I draw this out, this looks beautifully symmetrical here. So we're going to expect, if all of these atoms are equal and they all have the same size dipole moments, and they do because they're all chlorines compared to sulfurs. So if chlorine has a bigger electronegativity than sulfur, which it does, it's going to get slightly negative and sulfur is going to get slightly positive. So the center of all the positive is in the middle of the sulfur, and the center of the negatives will actually end up being in the middle of the sulfur as well, because they all balance each other out. So this molecule, because it is symmetrical, the atoms are arranged symmetrical, the dipole moments specifically are arranged symmetrically, then we have the positive pole and the negative pole exactly in the same place. Now you could say, remember, I haven't written this down, but you could write this down, that these negative and positive poles cancel each other out. But the reason it's called non-polar is because there are no poles, because the poles are in the same place. So actually when the poles are in the same place, they cancel out and there are no poles. So you can easily see what is polar and what is non-polar if you take into account the dipole moments. I hope this video has been helpful and that you're starting to understand how dipole moments can be used to identify the polarity of molecules. Now if you still want to use the explanation that I've taught you in a previous video, which is how bond dipoles and how they arrange symmetrically and asymmetrically produce polar and non-polar molecules, you're free to go and do that, that's fine. But always remember about identifying and drawing these dipole moments, because there might be a question that someone asks you in an exam about this, and you also might want to use this to check that your other answers are correct. Hopefully this has been helpful, and look out for my next video.